In this video, I'm going to talk about inverse matrices and determinants. But before getting onto that, let's just look at the words inverse and identity and see what they mean. If we look at normal addition with numbers, then a plus 0 is a. And this works the other way around, 0 plus a, and we say that 0 is the identity. Then, if I take a number like, say, 3, if I add minus 3, I get 0. I get back to the identity. We say that minus 3 is the inverse of 3. The same idea is true when we multiply. If we take a times 1, that is a, which is the same as 1 times a. And in the same sort of way, we say that 1 is the identity. If we take the number 3, multiply by 1 over 3, we get back to 1. 1 is the identity, and we say that 1 over 3 is the inverse of 3. If we look at matrix multiplication, we can see that if we take the matrix A, B, C, D, any matrix, and multiply by 1, 0, 0, 1, AB times 1 naught is A, and so on. This just leaves us with A, B, C, D. So in exactly the same way, with the multiplication of numbers, we get that 1 naught, naught 1 is the identity matrix. And we can write mi equals m, and that we could show is the same as im. Well, how can we find the inverse of m? If we're looking for the inverse of m, then we're looking for a matrix, if we think above, that the matrix or the number times its inverse brought us back to the identity. So we're looking for combining m with its inverse to give us the identity. How can I find m? We have the matrix M, A, B, C, D, and we're looking for a matrix M inverse to bring us back to the identity. Let's call the inverse matrix E, F, G, H. Then we're trying to find values for E, F, G, and H so that this equation works. Multiplying together, we get and if we look at the top line, we get, and if we look at the bottom line, and if we now take d times equation 1 and subtract b times equation 2, d times 1 minus b times 2 will get rid of the second term, and we're left with a, that's not a very good a e d minus c e b equals d times 1 d. And that gives us that E is equal to d divided by AD minus BC. I could also show in the same sort of way that F is minus B over AD minus BC, G is minus C over AD minus BC, and H is A over AD minus BC. Putting these all together, we get that the inverse matrix of M, EFGH, is D over AD minus BC, minus B over A, and so on, as you can see written there. And so M inverse I can now write as 1 over AD minus BC times D minus B minus CA, and this is the inverse of ABCD. Well, it's quite a simple process to write down the inverse starting with A. Firstly, we need this number here, AD minus BC. It's a sort of cross product, AD minus BC, AD minus BC. This is called the determinant. We'll come to that more later. So having found the determinant, then notice on the leading diagonal, we have just interchanged A and D. And on the other diagonal, B and C have become minus B and minus C. To summarize this, if we've got a matrix M, which is A, B, C, D, up here, then the determinant of M is written either as det M, two straight lines M, or two straight lines A, B, C, D, and it's equal to AD minus BC. Then we can go ahead and find the inverse of M as follows. Find the determinant. If the determinant is 0, stop. There is no inverse. If that's the case, if the determinant is 0, M is called a singular matrix. If the determinant is not 0, M is called a non-singular matrix. So that's step 1. It's sensible to do that first, because if the determinant is 0, you just stop. Step 2, we swap A and D, so A and D are swapped, and we change the sign of B and C. Step 3, we simply divide everything right through by the determinant. With the inverse, the order in which you multiply does not matter. M inverse M is the same as M inverse, which is the identity. We now do one important result in matrix algebra. If we're looking for the inverse of Mn, then you might think that the inverse of Mn was, woohoo, I just lost it. You might think that the inverse of Mn was M inverse N inverse. This is not the case. The inverse of Mn is N inverse M inverse. We do have to twist the two round. Well, let's prove that. If we're looking for the inverse of Mn, then Mn inverse combined with Mn must be the identity. This is how we define what's meant by inverses. So we can really write that as Mn inverse Mn equals I. Now remember that matrix multiplication is not commutative. We cannot swap the order around. If I decide to multiply on the right-hand side here, I should multiply on the right-hand side here. In this case, it doesn't actually make any difference, but it's good to be in the right habit. So what I'm going to do is to multiply both sides on the right by N inverse. The board has a mind of its own, it's moving around. Let's just make that a little bit better. Mn N inverse, I N inverse. Well, what's that going to be? N inverse here is just the identity. And multiplying anything by the identity doesn't change it. So on the left-hand side, we're going to have Mn inverse M times the identity, which doesn't have an effect. On the other side, I times the inverse of N is just going to be the inverse of N. Now it really does matter when I start multiplying. I'm going to multiply on the right, both sides on the right, by the inverse of M. So let's write the inverse of M, the inverse of M. Now we're nearly there. We've got Mn inverse multiplied by M inverse is just the identity, so that doesn't have any effect. And on the other side, we've got N inverse M inverse. And so we've proved what we wanted to do, that the inverse of Mn is N inverse M inverse. There is more about the algebra using inverses of matrices in your book FP1 on pages 95 to 98.